Yes, good afternoon, everybody, and good morning, Ros. It is a great honor to me to be the facilitator of this seminar. This is Junichiro Kuroda at the University of Tokyo. So for starting the presentation, please let me make a brief introduction of today's speaker, Dr. Rosalind Coggon. She is a Royal Society University Research Fellow within Ocean and Earth Science National Oceanography Centre Southampton at the University of Southampton. And as Taira-san said, she is the winner of the 2021 AGU-JpGU Taira Prize. So congratulations for the prize. And her research focuses on the role of fluids in the formation and evolution of the oceanic crust, with a particular emphasis on quantifying the thermally driven chemical exchanges between the aging oceanic crust and the overlying ocean water, and their influence on global geochemical cycles. She first sailed on a scientific ocean drilling expedition as a PhD student and is now co-chief scientist of the IODP Expedition 390 and 393, the South Atlantic Transect, that will recover complete sediment sections and upper oceanic crust along a crustal flow line across the western flank of the mid-Atlantic ridge to investigate a diverse range of interconnected Earth system processes. So, Ros, please start the presentation.
Thank you very much for the kind.
Sorry, this is an announcement that please turn off the camera just to keep the good internet connection between Japan and South Africa. So, Ros, please. Thank you for coming.
Thank you. Thank you very much for the kind introduction. And yes, I'm in South Africa, not Southampton today, because I'm actually quarantining in a lovely hotel room that I've been in now for a week, because on Saturday we will actually board the J-DESC Resolution to start Expedition 390. So we're very excited to finally go to sea. And in fact, people higher up in the hotel who have a view have seen the ship coming into the port this morning. So that's very exciting. The internet connection isn't brilliant here in the hotel. So please do interrupt me, Kurada-san, if there's any problem that you can't hear me, because I won't be able to know unless you tell me. So do interrupt me if there's a problem. And I'm going to turn off my own camera and share my screen in the hope that it will all work fine.
Hey, thank you.
I'm just sharing the screen now. Hang on. There's also a little bit of a time delay between here and Japan, I think, because of the slow internet. So I'm sorry if there's a bit of a time delay, but hopefully you can now see my starting slide.
Yes, we can see it.
Yes.
So today I'm going to talk to you a little bit about how drilling transects of sites can help us to explore the interconnected Earth. And I wanted to start with a picture of the new science framework for the next 3 decades of scientific ocean drilling, and have a little think forwards before we look back at what ocean drilling has already done and what we're about to do, to think about how we can advance our understanding of Earth as an interconnected system, which is the overarching goal of the new science framework. And in particular, I want to talk about how changes in ocean chemistry reflect the shifting balance between interconnected fundamental Earth processes. So ocean chemistry can tell us a lot about different parts of the Earth system. And from my point of view, what I find interesting is that the igneous crust that forms the basins that hold the oceans is not just an inert container. In fact, the entire volume of the oceans is circulated through the upper oceanic crust on the ridge flanks every few 100,000 years. So there are lots of interconnected processes that we can look at by investigating the ocean crust. And that is because the fluids that circulate through the ocean crust react with the rock and leave a fingerprint of ocean chemistry on the rocks. And cores of the ocean crust recovered by scientific ocean drilling have revealed that the ocean crust preserves records of past seawater chemistry and can also be used to investigate a wide range of interconnected Earth processes from such records. So here is a core of hydrothermally altered ocean crust. This is the sort of material that I'm going to be talking about today. Here you can see a basalt core with carbonate veins through it and alteration halos, and we'll have some more similar rocks to look at as we move forward. But first of all, let's think about why the ocean crust is important. So the formation and aging and destruction of ocean crust is part of Earth's largest scale cycle of energy and matter. The ocean crust is a key boundary between Earth's interior and the oceans and atmosphere, through which energy and matter are transferred. And these exchanges of energy and matter through the ocean crust leave signatures in the ocean crust that can be used to investigate how Earth's chemical reservoirs have evolved over time and what processes have been responsible for those changes. Thermally driven circulation of seawater through the cooling ocean crust is a vital Earth system process. I've got a little video here of the type of hydrothermal circulation we're used to seeing. This is the spectacular hot black smoke event on the ridge axis. And this process is important because it influences tectonic, magmatic, chemical, and microbial systems on a global scale. The high temperature hydrothermal circulation that we saw in that video during the accretion of new mid-ocean ridge crust is intimately linked to the magmatic accretion and the architecture of the ocean crust, as the extraction of the heat by the fluids influences both the spatial and temporal distribution and the depth and the geometry of magma chambers in the crust. And the biogeochemical exchanges between the crust and the fluids influence ocean chemistry over time as well, controlling the long-term geochemical evolution of the oceans and the atmosphere, the lithosphere, and the mantle as a result of subduction. So this is a really important process that we want to understand. How does the ocean react with the crust as it passes through it? Ocean chemistry is also really important. It reflects a balance between things that are being added from the continents by rivers, the removal of material and burial of it in sediments, as well as the hydrothermal exchanges between the oceans and the ocean crust. So you can see all those parts of this cycle here. And over time, the balance between these processes has shifted. And so if we look at records of past ocean chemistry, here we see a record of the past strontium isotopic composition of the oceans. And in this case, this is a balance between the amount of material being added from the continents, which adds radiogenic strontium to the oceans, and the amount of material being added at the mid-ocean ridges, which will add mantle strontium to the oceans. So records of past seawater chemistry can provide integrated records of a range of fundamental Earth system processes because of the different components of material being added to the oceans. For example, mountain building, erosion, weathering, changes in the rates of ocean crustal production and subduction, large igneous province emplacement, changing climate, and the evolution of biological systems are all going to affect ocean chemistry with time. So if we can construct records of past ocean chemistry, we can then begin to decipher them to understand how these different processes have changed and evolved as Earth has evolved. The traditional approach to deciphering past records of seawater chemistry has been to try to estimate what is being added to the oceans from the rivers. However, the chemistry of major oceans currently draining the continents may not be representative of material being added in the past, particularly for elements whose residence time in the ocean is greater than interglacial glacial cycles. And that's where quantifying hydrothermal contributions comes in. So if we can quantify the material being added from the ocean crust or taken up by the ocean crust with its exchange with seawater, then we can remove the hydrothermal component to seawater records of chemistry and then look to see what else must have been changing to cause the remaining signatures that we see. Hydrothermal signatures ought to be easier to quantify because the ocean crust is geologically young and chemically relatively homogeneous compared to continental crust. And so the reactions are relatively well known. But crucially, the effect to which hydrothermal circulation is going to affect ocean chemistry depends on the amount of fluid that is passing through the crust and the extent to which its chemistry is changed as a result of reaction with the ocean crust. This is perhaps easier to work out on axis where we have the types of venting springs that we see on axis, because we can collect samples of the fluid using submersibles and then analyze it and compare it to seawater to see how its composition has been changed as a result of fluid rock reaction. And we can also make estimates of the amount of fluid that is coming out of these systems from heat budgets and from sampling the vents and their temperatures. However, we also know that there is what is called the conductive heat flow anomaly extending off axis that tells us that there is actually hydrothermal flow happening not just at these high temperature systems on axis, but continuing off axis. So what we see here is the predictive heat flow that we should see, conductive heat loss that we expect to see through the seafloor as a function of age as it cools after accretion, versus observation of the actual conductive heat flow, these red squares across the ridge flanks. And what we see is that there is a difference. There is missing heat here, and the heat that is not being conducted out of the ocean crust is attributed to advective heat loss or removal by fluids, which indicates that there should be fluid flow out until about 65 million years. And because this is happening at much lower temperatures, it requires a much larger volume of fluid. But these fluids that are low temperature and diffusively vented are very hard to sample, and therefore it's not possible to estimate the contributions by simply sampling the fluids and measuring the amount of fluid coming out of vents or estimating it from heat budgets. So what can we do to try and work out the extent to which this hydrothermal exchange happening on the ridge flanks might be affecting ocean chemistry? Well, the answer is that we can look at sections of hydrothermally altered ocean crust, because they record the time-integrated effects of fluid rock exchange. So this is an example of a basalt cord on the Wonderfuka ridge flank. And rocks such as this record time-integrated records of fluid rock exchange, key parameters such as the fluid flux, the composition, and the flow pathways recorded in the rocks. And by working these out, we can then try to work out the hydrothermal contributions. The hydrothermal alteration is manifest in the formation of secondary minerals, and these might form in the ground mass, in the primary, replacing primary minerals. They also form in the vesicles. You'll see in a minute from a thin section photograph, but there are secondary minerals filling and lining some of these vesicles. And secondary minerals also form along cracks in the rock, forming veins. In more spectacularly altered rocks, this is a higher temperature rock from deeper in the crustal section. We see breccias, mineralized here with sulfides. In some cases, this is back in the lavas. We see evidence of the fluid rock interaction extending beyond the fracture. So here we see a vein filled with secondary minerals, but there is what we call an alteration halo around it, where there has been interaction between the fluid flowing through the rock and the walls of the fracture, with a progressive alteration, a chemical change happening away from the fracture. One of the things that we can do to work out the extent of chemical change is compare fresh portions of the rock with altered portions of the rock. So here we actually see part of a pillow lava, and this is actually the fresh glassy rim of the pillow lava. So by taking samples from this rim, we can determine what the composition of this rock was before it interacted with seawater. And then by taking samples that are from adjacent to the fractures where fluid flowed, we can do a comparison to work out how the chemistry was changed as a result of that interaction. The types of secondary minerals that form don't just tell us about the changing composition, but they can tell us about changing conditions within the rock. Different minerals form at different temperatures and under different conditions, and we can work out how those have changed sequentially. For example, from a vesicle fill, where different minerals form progressively as the conditions within the rock changed. We can also use a wide range of other properties of the rocks to investigate the nature and extent of hydrothermal alteration. So here we see some data from hole 504b, one of the classic sections of upper ocean crust. And some of the things that we can measure to understand the extent of alteration are the proportions of different features. So what volume percent is actually breccia, and what are the secondary minerals that form that breccia matrix? How many veins are there in the rock, and what is their volume percent? What proportion of the rock is made up of different types of alteration halos that are these intense zones of fluid rock reaction around the veins? Again, we can also map the actual secondary mineralogy that we see in the cores with the different minerals reflecting different physical and chemical conditions. So here we see a shift as we go deeper in the section from minerals that would have precipitated during cooler, more oxidizing conditions, and then minerals that are higher temperature minerals precipitating as the fluids get deeper in the crust, interact with the rock and heat up. We can also analyze various chemical properties of the rocks, major and trace element concentrations or isotope ratios. Here I'm just showing you potassium, and these various traces tell us about different aspects of the fluid rock interaction. In this case, we see that the fresh rock would have had very low potassium concentration, but the addition of potassium from seawater has changed the composition of the rocks, and this effect decreases with depth as the seawater that reaches these depths is more evolved. And by combining all these different analyses, we can actually calculate the extent to which the net effect of this alteration would have had on ocean chemistry. So we can look at the compositions of different features, different things that make up the core, and then make a mass balance looking at the proportions of those features in the core to work out the bulk changing chemistry of the whole section. And then by extrapolating these using crustal production rates, we can actually look at the amount in terms of moles per year that each element is being either added to the ocean crust or removed from the ocean crust. So you can see the biggest change here for 504b is the amount of water that's being added to the crust, and that shouldn't really be a surprise. But we need to sample crust from a range of settings to understand the controls on the nature and extent of hydrothermal alteration. We already know from our limited sampling of different spreading systems that the architecture of the ocean crust varies with spreading rate. For example, even just in the upper crusts, we think that at faster spreading rates, there is a higher proportion of sheet flows and even massive flows, whereas at slower spreading rates, as you see here, just looking at fast to intermediate, a higher proportion of pillow lavas. And these differences in the morphology of the lavas also affect the permeability of the crust. The lavas provide many more pathways for fluid to pass through the crust, and that is reflected in the alteration of the crust. So here we're looking at 504b, 896a, and 1149, which are three different sites produced at intermediate rates. And we see that there is a much higher percent of oxidizing alteration halos in these rocks compared to sections of fast spread crust where the lithological structure of the whole might impede fluid flow. So spreading rate is obviously important. Crustal age is probably also important, and also sediment cover and sediment thickness composition. So we need samples from a wide range of settings. However, one of the problems that we have is that we know that fluid flow is probably happening up until at least 65 million years, probably longer if there are places where the fluid can access the crust and bypass the impermeable sediment cover. But we have a lack of samples of old ocean crust. So the extent and duration of hydrothermal exchanges in aging ocean crust remain really poorly quantified. This is a figure that's actually taken from a workshop that was held in support of mohole drilling and a proposal to drill on the North Hawaiian Arch that is being led by Japanese colleagues, in particular Amina-san. And what this shows is that our deep sampling of the ocean crust in particular is limited to very young crust. But even just sampling the upper ocean crust, we have a range of samples in young crust. We have some limited sampling of old crust, but we have almost no samples from what I would call middle-aged crust. And this is really important because the average age of the ocean crust is about 63 million years. So we don't have any samples that tell us what average ocean crust would look like. And the average age of subducting ocean crust is about 80 million years. And knowing what is going down the subduction zones, both what its chemistry and physical properties are, is really important to understanding subduction zone processes, the generation of hazards, and also the effect of subduction on geochemical cycles and mantle chemistry. And so this is a really important age. And in fact, this is the age of crust that the proposed Hawaiian North Arch drilling will sample. And of course, there are strong reasons to drill there in terms of understanding crustal structure and trying to reach the moho. But from my personal perspective, it is also a really important place to drill because it will provide the first samples of ocean crust that should be representative of what is currently going down subduction zones. Crucially, the age and the age area distribution of the ocean crust has varied with time. And this is because both the global ridge length and average spreading rates have changed. So at the moment, crust is being produced on average about 3 kilometers squared per year across the whole planet. But 120 million years ago, there was on average 5 kilometers of ocean crust being produced each year. And so as a result, the average age of the ocean crust has changed with time. And if the temperature of the fluids circulating through the crust decreases as you move off axis, then the average temperature at which hydrothermal exchange has been happening will have also changed through time. So it's really important to understand how that will have affected the global contributions from the ridge flanks to the oceans if we want to understand past records of ocean chemistry. But if we do get records of past crustal production and combine them with knowledge of the controls on the nature and extent of alteration, then we can use that information together, predict those contributions to hydrothermal contributions to seawater chemical budgets, and then begin to interpret what else must have been happening in the Earth system to produce the records of ocean chemistry that we see. And that brings me to my other interest in ocean crust. We know that the continuous repaving of the ocean floors with igneous rocks provides continuous records of Earth's magnetic field. This is the Vine-Morley-Matthews hypothesis. They noticed that there was a symmetrical pattern of magnetic stripes on either side of the mid-ocean ridges, and they hypothesized that this was a result of Hess's seafloor spreading proposal, hypothesis. But cores from scientific ocean drilling have revealed that just as the cooling crust preserves this signal of Earth's magnetic field as the crust cools and moves away from the ridge axis, the ocean crust also records changes in the ocean chemistry as it reacts with different seawater as the seawater evolves with time. And this led to a dramatic shift in the appreciation of studies of hydrothermally altered ocean crust, as they enabled us to both reconstruct ocean chemistry and decipher the changes in those records that are recorded. We heard at the beginning that there is a long-standing observation that cores of Cretaceous and Jurassic ocean crust actually contain more abundant hydrothermal calcium carbonate than young ocean crust. So here we see a plot of the bulk CO2 content of ocean crust versus crustal age, and the old crust contains more carbon than the young crust. And this was, for a long time, this was assumed to just be a result of the progressive alteration of the ocean crust. So here we see a photograph of a 7 million year core with a small amount of carbonate in it. And you can see the much greater volume of carbonate in this 132 million year crust. And it was assumed that as the crust gets older, more and more carbonate builds up because fluid flow continues through the rocks. However, various lines of evidence indicate that carbonate precipitation happens relatively early. And perhaps the most compelling is this evidence from direct uranium-led dating of hydrothermal carbonate veins. So here we see the age of the host crust, and here we see the age that has been determined of the veins. And the majority of those veins are forming within 20 million years of the crust that they are hosted in, which suggests that carbonates precipitate relatively early. And if that's true, then in fact, we would see trajectories like this, where crust accumulates carbonate, the crust accumulated the carbonate relatively early and then stayed unchanged for the rest of its life. And this would be consistent with the hypothesis that variations in the nature and extent of hydrothermal alteration are recording changes in the Earth system. In particular, in this case, the changing levels of atmospheric CO2 have changed the amount of CO2 that is being taken up in the ocean crust. There's a feedback here. So in the Cretaceous, when CO2 was higher in the atmosphere and hence in the oceans, and the oceans were warmer, which enhances hydrothermal alteration, there would have been more carbon uptake. And now I want to talk a little bit about drilling transects. So drilling experiments across the Wondafuka ridge flank were designed to investigate ridge flank hydrothermal circulation and crustal evolution. ODP Leg 168 used the transect approach to investigate this. They drilled 10 holes along an 80-kilometre transect with shallow penetration up to about 50 metres into the underlying basement from ages of about 0.8 million years out to 3.6 million years. Crucially, they also installed a series of corks at some of these sites. In IODP Expeditions 301 and 327 revisited this area in 2004 and 2010, drilling deeper into the base, adding further corks and conducting in situ hydrogeologic and microbiological experiments. So here we see one of the cork systems that was installed. And for those who are not familiar with these are literally a cork in the hole. You put a bung in the hole, and then you can have an instrumented string down into the borehole so that you can measure in situ conditions like temperature and pressure. And you can also collect fluid samples from the basement. You can also do in situ microbiological experimentation as well. So those sites with red arrows were the ones that received corks. And what the sampling of fluids from these cork systems revealed was that there is temperature-dependent fluid rock reaction in the basement. So the sites with red lines here are the ones that had corks. And in addition to the fluids that were sampled from the corks, we can also use the samples of fluid right from the sediment basement interface and assume that there is communication in the fluid across this critical transition that allows us to sample fluids from the basement, because we can't squeeze the basement rocks to get the fluid out of them, but we can squeeze the sediments. And what the Wonderfuka experiments revealed was that there is an increase in temperature, and as there is an increase in temperature, as fluids move away from places not just near the axis but also seams where they can get into the basement, the fluids heat up. So this results in a decrease in the strontium isotope composition towards more values as the fluid is heated, and also a decrease in the fluid's magnesium concentration, because magnesium is being incorporated into secondary minerals, particularly clays and also carbonates in the ocean crust. And what I was able to show in some of my previous research was that the calcium carbonate veins from those basalts record the same temperature-dependent evolution as the ridge flank hydrothermal fluids they come from. So here we see a sample of basalt from the Wonderfuka Ridge with carbonate veins. It's broken along the vein surface. Here we see the strontium isotope composition of those sampled ridge flank fluids, modern seawater. And if we look at the composition of the carbonate veins, there's no fractionation of the strontium isotopes when the carbonate precipitates. So they're recording the fluid that they came from. We see the same temperature-dependent fluid evolution in the basement veins as we do in the sampled fluids. And crucially, that trend can be traced back to modern seawater. So we have a model where cold seawater enters the permeable ocean crust, circulates through the crust and is gradually heated, indicated here by its changing color. And along the way, precipitates carbonate veins that are recording its progressive chemical evolution. And this isn't just seen in the strontium isotopes, we see it in the major element chemistry too. Here we're looking at the strontium-calcium ratio, and this is the strontium-calcium ratio of the fluid. So from the carbonate veins, we use a partition coefficient to calculate the fluid ratio, trace element ratio. And again, we see that these project back to modern seawater. This means that carbonate veins in ancient ocean crust also have the potential to record past seawater chemistry, provided that we can account for this changing composition as the fluid reacts with the host basalt. And what we did was we took sweeps of veins from ancient ocean crust, and here I'm just showing you 110 million year crust. And we did the same calculations to work out the chemistry of the fluids they precipitated from, and we project those back to the temperature of contemporaneous seawater, and we see that we can in fact reconstruct the strontium isotope ratio of the fluid that was evolving, which allows us to use the seawater strontium isotope curve to get the age of this suite of veins, and also the past strontium calcium ratio. And by doing this for a range of sites, we can actually put together records of past seawater chemistry. You'll see that the magnesium calcium ratio record that we put together for veins is in good agreement with the records from fluid inclusions in evaporites and also from well-preserved echinoderms. The The record that we have for strontium calcium is quite different to the biogenic record, which suggests that there's something else going on that we've not entirely worked out yet, and is most likely due to uncertainties in seawater shell partition coefficients, or perhaps poorly understood physiological effects. Either way, what these various things that I've presented show is that hydrothermally altered crust can both yield records of past seawater chemistry and be used to decipher those records if we quantify the hydrothermal contributions to the oceans. But all of this requires that we drill middle-aged crust. This is something that was recognised when the current science plan was written, calling for a series of ocean-wide transects along crustal flow lines. And the importance of drilling transects has been recognised for since the very beginning of ocean drilling, when Leg 3 in the South Atlantic drilled a series of sites across the South Atlantic to prove the theories of plate tectonics and seafloor spreading. And they did this by coring a series of spot-cored holes either side of the ridge, and by measuring the age of the sediments at the bottom of the holes and showing that these increase systematically and symmetrically away from the ridge both sides, which showed that the crust must also be getting older both sides of the ridge. And you can see that here, that the distance from the axis sediment age increased. And so we are about to embark on expedition 390, which is the first of two expeditions. 393 will follow immediately after us, to investigate multidisciplinary aspects along the same crustal flow line that Leg 3 visited in the southern mid-Atlantic ridge. In particular, we're going to investigate the hydrothermal evolution of the aging ocean crust, the microbial community variation with increasing substrate age, and the paleoceanographic evolution of the South Atlantic Ocean recorded in the overlying sediments. Our proposed strategy exploits targets that will therefore simultaneously address multiple of the IODP science plan themes and maximize scientific output for the drilling effort. We are revisiting the Leg 3 area, but we have adjusted things slightly. So we have a new site survey that was conducted on the Marcus Langseth in 2016, led by Bobby Rees and Gail Christensen. And we have identified 5 different ages of crust that we want to investigate. We have adjusted, so the orange dots here show the Leg 3 sites and the black dots show our sites. And we've adjusted our sites to put them on a single crustal flow line because we want to investigate crust that was produced at the same spreading ridge segment, so that we should remove ridge segment variations from the things that might be changing between sites, so that we can investigate just the effects of the crustal aging rather than magmatic effects due to different segments. We've also chosen sites that have as close as possible to a 20 millimeter per year half spreading rate, because we particularly want to investigate slow spread crust, because this is undersampled in our current sampling of ocean crust. And we have, as I said, 3 overarching objectives. This figure shows a schematic architecture of mid-ocean ridge flank and illustrates various parameters that might influence the intensity and style of alteration, with the red arrows in this cartoon indicating heat flow and the blue arrows indicating where there might be fluid flow across the ridge flank. But as you'll see, there are a lot of question marks. We don't know the extent to which basement topography might affect fluid flow. We don't know what the limit of life is across the ridge flank. And most of this is because we have limited sampling. And so our sites will start to fill in a systematic way these gaps in crustal sampling and allow us to answer questions regarding when exchange is happening, how long for, and how much. Our sites also traverse the previously unexplored biosphere of the low energy South Atlantic gyre. This map shows the locations of all the ODP and IODP holes up to 2014. It is, of course, now out of date. But the key thing here that hasn't really changed is that the larger circles represent samples that sites where there has been microbiological sampling. And what has not changed is that the majority of sites have not been microbiologically sampled because they were drilled before such investigations were conducted. And crucially, there are no microbiological investigations in the South Atlantic. So in order to answer questions regarding global biomass, the extent to which biomass varies from region to region, we need samples from this area. We also want to investigate how the aging ocean crust is altered by microbes, the role of those microbes in geochemical cycles, and the extent to which the communities change as the substrate changes. The sediments recovered along this transect will also allow us to investigate the paleoceanographic evolution of the South Atlantic. On the left here, you see the composite deep sea benthic foraminiferal carbon and oxygen isotope records, and they show both gradual and abrupt changes in global climate during the Cenozoic. There are various events here that you can see picked out. And over here on the right, you see the parts of this record that we expect to recover at our various drill sites, with blue indicating the portions of each site that we expect to find carbonate-rich material that accumulated before the ocean crust on which it sits was thermally subsided below the CCD. And by combining these sites together, we expect to recover a rich paleoceanographic record that will allow us to create a megasplice in a similar approach that was used for the Pacific equatorial age transect sites on IODP Expeditions 320 and 321, and answer a range of questions about how the South Atlantic responded to climate events, both local and global, and how it responded to changing ocean current patterns. We're going to be drilling at 5 different crust ages, although we actually have 6 sites because we have 2 sites at our oldest age of 61 million years that will allow us to investigate the effect of different sediment thicknesses. So here we have a thinner sediment than at this site, how that might affect hydrology of the ocean crust and the extent of alteration. So we go from east here to west. We have these 6 sites spread across 5 crustal ages indicated in red. And we were obviously unfortunate to be hit by the COVID pandemic. We were supposed to be out at sea in 2020, but we are very fortunate that the JRSO has managed to conduct engineering work towards our expeditions already. And so in fact, you see here our drilling strategy of installing a re-entry cone at each of our crustal layers that will allow us to re-enter the hole and drill 250 meters or more into basement, as well as recovering 3 sections of sediment at each crustal age to allow us to do our sediment microbiological and paleoceanographic objectives. And the engineering expeditions 390C and 395E that have already been to sea have already done a lot of the operations in terms of installing the re-entry systems and drilling 1 sediment hole to allow us to do the safety measurements required for that work. So we already have some cores, and here you can see some beautiful samples of the sediment basement interface of brecciated hydrothermally altered upper ocean crust. We've penetrated about 5 meters into the basement so far, and hydrothermally altered basalts that are going to be really important. So we'll be back out at sea next week to do the rest of our drilling, and then we'll be able to share results with you soon. I just wanted to come back to the science framework to end my presentation, and in particular to say that one of the fundamental differences between this new science framework and the previous science plan is its focus on understanding the interconnected Earth system rather than dividing our science into distinct themes. And of course, it's much longer 3-decade outlook. As I've illustrated with some of the transects that have previously done by ocean drilling, so that would be the Leg 3 transect back in the early days of DSDP, the work on the Wonderfuga Ridge flank, and now our drilling on the South Atlantic Transect. Such transects can transform our understanding of Earth as an interconnected system and offer really valuable opportunities for multidisciplinary investigations. However, as you've also seen from those expeditions, multiple drilling expeditions are usually required. And the good news is that the longer time frame, those 3 decades of the new science framework, will allow us to formulate more ambitious drilling strategies that might require multiple expeditions using 1 or more drilling platform to drill either intensively in one place if we were trying to drill a really deep hole, such as a mow hole, or to drill a transect of sites to answer a range of questions. And this is really exemplified by the flagship initiatives of the framework, which will certainly require multiple coordinated expeditions. And just as an example, probing the deep Earth will require both a series of holes and a concerted effort to drill deep, and or a series of holes in a transect across tectonic windows, ideally both, so that we can compare fast spread crust, which is generally less tectonically disrupted, and slow spread crust. So the mow hole drilling effort is going to be really important to addressing the ongoing science framework. So we're going to need to plan multidisciplinary drilling expeditions to get all this done, such as the South Atlantic Transect. It will also allow us to develop efficient and effective strategies that are sustainable, which is going to be increasingly important as we move into the future of our planet. And now, if you'll indulge me, I am finishing, I promise. I just want to take a moment to think about what ocean drilling has done for me. And this is really particularly aimed at maybe any younger members of the audience, because it's now 20 years since I first boarded the JR. I sailed on leg 206 back in 2002, and this was the start of the efforts to drill to the Dyke-Gabbro boundary in situ crust. So probably consider this the first effort to try to drill to serious effort to try to drill to the mohole. And the first task was simply just to try and penetrate the entire upper ocean crust in one place. And the logic here was to exploit an observed relationship between the depth to a seismically imaged magma chamber and spreading rate. So if we exploited this relationship by drilling at the fastest spreading rate possible, we ought to encounter these magma chambers at the shallowest depth. But going to sea wasn't just part of an exciting science project. It was fantastic to work as part of an international team and feel like I was part of something big. It was fantastic to learn new things. I was given responsibility for writing the sedimentary section, well, volunteered maybe, as there was no sedimentologist on board, but it put me in a position where I could learn new things and take on responsibilities despite being a first year PhD student. And in fact, within 18 months of starting my PhD, I had returned from sea and was a proponent of a proposal to return to this hole and deepen it. And you can see the co-chiefs here and staff scientist, and also one of the galley staff very excited about our long pieces of core. I then sailed on 301 to the Wonderfuka ridge flank, and this was really interesting from the point of view of learning about the engineering involved in installing corks, and also being given even greater responsibility, still a PhD student. And then as I was finishing my PhD, we returned to 1256D, so our proposal was successful and we had 2 expeditions, 309 and 312. And I sailed on the latter, which was the last expedition of the first phase of IODP. And it was memorable not only because I finished my thesis on the ship on Christmas Day, but also because we reached the Dyke-Gabbro boundary that we had been searching for. You can see it here in thin section. Here is a fine-grained dike, and here is the top of the Gabbros. And perhaps not politically correct, but here you can see me putting a flag in that boundary. But in seriousness, this was really exciting. This was ocean drilling, allowing me to go to a part of the planet, to the in situ boundary between dikes and gabbros, the base of the upper ocean crust, that no one had ever been to before. People who may have put their finger on it in an ophiolite, but this was the first time we had been there in real in situ ocean crust. And hopefully, some of you on this call might be involved with the time when we finally get to the moho, not necessarily at site 1256, but at another site, we reach the mohole, and you'll be able to put your finger on that boundary and say that you were there the day that mankind finally reached the moho for the first time, which I think is an absolutely exciting, beyond words actually, prospect. So in summary, what has ocean drilling done for me? Well, you work as part of an international team and you really do learn from the best. You spend 2 months with them intensively. You build friendships with them that last for life. It's certainly been career building. I've built my career out ocean drilling since those early days in my PhD. It has allowed me to be part of something big. It's like being part of the space program. It is enormously exciting. Of course, you make friends with the people that you live with on the boat. You have adventures both at sea, but also when you travel to the boat and explore all different parts of the world. I think I've sailed through the Panama Canal twice now on the JR, which I would never have done if I hadn't been involved in ocean drilling. It's certainly allowed to be an explorer, not just around the globe, but also into the subsurface of the planet. Maybe not quite a journey to the Earth, to the center of the Earth, but I feel like I'm on the way. And finally, it's allowed me to contribute both to our understanding of the planet, to the program itself, but also to maybe to knowledge that will help us as a human race look after our planet better in the future. And with that, I'd like to end there. Thank you.
Thank you very much for excellent talk. It's very, very interesting. Thank you very much.
I'm sorry that I went over time. Thank you very much for staying to listen.
As Ross said, introduced, now the Science Framework 2050 has been published last year, and it's available online from the IODP website. And Ross is one of the lead editors of this book. This is very nice book, and not for learning but also reading to understand how the recent science progress is, how to say, accelerated by scientific ocean drilling. So please, if you haven't read it, please download and take a look at the book. Okay, Ross, thank you very much. So now the time for discussion. If you have questions, please put your mic on and talk to Ross. We encourage, especially for young people who make to make a question, but also aged people are also welcomed. So I have a question. Is everybody okay? Taira-san, please.
Aged person is okay. Am I allowed to do that? You mentioned the integration or the more interdisciplinary aspect of the future ocean drilling, and I think I completely agree with we have to solve more Earth system behavior. But at the same time, I think you mentioned on your study, to me, it's finding the end member. Could be important. For example, you mentioned the finding fresh pure basalt and compare with the altered basalt and veins could be important because it requires it really solves some of the problem of the initial condition to the aging, the alteration and so forth. So it's came to my mind that I think your expedition is closely related to the 391. Maybe I'm wrong in number, but there's a Walvis Reach Seamount Chain Expedition, which take place coordinated. I don't know how it's get coordinated, but Seamount basalt provides you the other end member, and some of the margin of the seamount may not be hydrothermally altered, which been exposed to the seawater more or less constantly, and the more inside of the seamount, maybe the low temperature alteration may be taking place, but the initial hydrothermal activity could be much less than Reach Flank basalt. So to me, if you compare the seamount basalt study and then at the same time with your transect, could yield something could be interesting. What do you think?
So I've lost the end of that, the video phrase, but I think I got the gist of it. So yes, comparing with the seamounts will be really important. Not just for my work. So any basalt that has seawater going through it, you would expect a cool reaction because carbonates can form when the seawater is barely heated above its initial temperature. So anywhere where basalt is exposed, you would expect to precipitate carbonate. So from my point of view, that's really exciting because anywhere I can collect carbonate veins, I can use those carbonates to reconstruct ocean chemistry. But in terms of the changing of the ocean crust, as a result of hydrothermal alteration, those seamounts are also really important, both in terms of the end member approach that you described, but also because it's possible that the seamounts are actually more hydrothermally altered than ocean crust that's covered by sediments, exactly because they stick up and that topography may channel hydrothermal fluids or seawater through them with a hydrological head. And so we may see more exchange. And so we really need to sample them as well to understand the role that they play in changing ocean chemistry and recording ocean chemistry. And then also we do have It wasn't in our original objectives for our current drilling, but we have scientists on board who are interested in understanding the role that the hotspot may have played in both causing the Atlantic to open in the first place and then in the evolution of the crust. And so they want to compare the samples of lavas along our transect where the ocean crust appears to be normal thickness and not influenced by hotspots, with samples that are recovered from the Walrus Ridge to see if they can work out the magmatic history of the Atlantic Ocean and the opening of the ocean from looking at that. So comparing with other expeditions in the region is going to be really exciting. Of course, when we wrote our proposal, we didn't know that they would be drilling there because their proposal came after ours. But now that there has been drilling there, and also they're recovering basement round on the Arguelles Plateau on the expedition that's just come in, there are lots of opportunities to actually compare with other things in the South Atlantic region and just round the corner the other side of South Africa. So it's very exciting.
Thank you very much. Looking forward to hearing further work from you.
Okay, thank you. Do you have any other question? I have a question about the diagram between strontium isotopes and temperature. That looks very clear to see two different trends. One is at Van de Fuca, the young one, and the other is more how to say not so steep.
Much shallower.
Cretaceous, shallower. Yes, Cretaceous trend is more flat. So what is the difference in those two, the slope lines? Are they a mixing lines?
So no, so the difference is that the strontium isotope composition of seawater has changed with times. So the strontium isotope composition of modern seawater is much more different to basalt. So basalt is around a 0.7025, 703, and stays that way because it's controlled by the composition of the mantle that is melting. Whereas over time, seawater has changed enormously. And at times like now, when the seawater is more different from basalt, there is a bigger driving force for reaction, so you will get a greater slope. The other thing that is different about the Juan de Fuca Ridge is that the Juan de Fuca Ridge is thickly sedimented when it is very young. So the crust is only up to 3 million years old. But because it is near the continental margin and there are turbidites coming off the continental margin, you build a thick sediment pile quickly. And so that allows the crust to conductively reheat below those sediments that are cutting up from the ocean. And so the fluids going through them are hotter as well. And so that enhances the reaction. So it's partly about the greater temperature range and partly about, I think, the difference in composition between the greater difference in composition between seawater and the rocks. And it was in fact those differences in slopes that made us realize that was the first thing that we noticed, that if the strontium isotope was different, it must be because the seawater had a different strontium isotope composition. And if that was true, then maybe we could look at other properties of the fluid chemistry to work out other compositions of ocean, in particular the strontium calcium and the magnesium calcium. So it was seeing that difference in trend that sort of triggered this whole discovery in the first place.
Yeah, thank you. And in your diagram, it looks like that the calcite is precipitated at higher temperature at Van de Fuca. Is that correct? So aragonite precipitated.
That is also a very good point. Yes. So aragonite is stable, is the favored precipitate at higher magnesium calcium ratios. And so in the modern oceans, aragonite would be the stable precipitate. But what happens is that as the fluid reacts with the basement, magnesium is being incorporated into the basalts as a result of clay formation, and calcium is being liberated. And so the magnesium calcium ratio of the fluid is decreasing as the fluid is heated. And so you actually reach a point where aragonite is no longer the favored precipitate, and in fact you move to calcite. So it's a bit like the alternations in aragonite and calcite seas that you would expect with time, except that it's happening in the crust all at one time. You heat the fluid up, you change its chemistry, and you shift from an aragonite sea in the basement to a calcite sea in the basement.
Oh, I see. Thank you very much.
From Cretaceous crust, they're normally calcite because it comes in already with a lower magnesium calcium ratio.
Yeah, so in the case of Cretaceous carbonate, it's almost precipitated as calcite, right?
Yes.
Okay.
Yes.
Thank you. Now I understand. So we have a question from Mari Hamahashi-san. Thank you for your great talk. Mari-san, can you speak or do I read your question?
Yeah, I can.
Oh, please. Thank you.
Thank you for a great talk. I was interested in your how you linked long-term carbonate precipitation from carbonate veins in the basalt versus long-term climate change, like the graph you showed, the change in CO2, for example. And it was kind of interesting for me because I've never really thought about hydrothermal alteration as means of carbon fixation in long-term scale in the carbon cycle. So I just wanted to hear your opinion about how significant that is. And I think the timing and cause of hydrothermal alteration and crystal formation seem to be very interesting also, given that a lot of CO2 should be released from the Earth's surface when there's active crystal formation. So I think you had a figure about linking the timing of hydrothermal alteration with crystal formation as well. So what is the timing and cause of it as well? So that was some of the points that I was interested in.
So I agree that it's really interesting. And in fact, that is one of the key things that I'm trying to investigate with my current fellowship and the reason why I proposed this drilling in the first place. So one of the things that I'm going to be analysing is the carbon content of the basalts that we recover from this intermediate age crust. And I'm also going to be collaborating with Michelle Harris in Plymouth to do uranium lead dating of the carbonate veins as well, to try and tie down how late after the crust is forming the carbonate is being taken up, so that we can work out the timing relationship between changing environmental conditions and the carbonate, so that we can try and work out both the extent to which this might be buffering CO2 in the oceans, and whether or not it is simply responding to changes in the Earth system. So as atmospheric CO2 goes up, does the ocean crust simply respond and incorporate more CO2, or is it really acting as a feedback? And it might be that what excites me is that it might be an active feedback in the Earth system, because one of the things that happens as you change the CO2 content is that, of course, we're also warming the planet, and so the oceans are warming too. And Rosalind Coggon has already done some modelling that shows that you would expect that if you put in if the seawater entering the crust is even 10 degrees warmer, that in itself, just putting in warmer seawater into the ocean crust, will enhance the reaction rate and cause you to form more carbonate in the first place. And so if that's really true, then there really should be this feedback between changes in atmospheric CO2, the temperature of the oceans, and then the amount of carbonate that you precipitate, which then, of course, takes up CO2 and has a feedback where you're then potentially decreasing atmospheric CO2 and cooling, and then less carbonate precipitation. So I can't answer your question about whether it is definitely happening yet, but I hope that once we've done this drilling and these analyses, that we will be able to say whether or not this is really having an effect. Previous studies have said that they thought that it didn't have a net contribution because the amount of CO2 being decast from the mid-ocean ridges was changing with time too. But actually, it's just really, really poorly quantified, because we just don't have the samples to really say the extent of CO2 uptake that there is as a function of time. And that's why we want to do this drilling, so that we can actually do that mass balance and say whether it's having an effect or not.
Thank you. I learned
I hope
a
that
lot
answers
from
your
your
question.
talk. Yeah. Thank you very much.
Okay, thank you, Hamahashi-san. Do you have some more questions? The time has already 1 hour has passed. So I can see one person who may be on board. 相沢さんいらっしゃいますか？相沢さん、can you speak? Because you will be on board for this expedition 390 with Ross. You are at the Cape Town, right?
You can see we have the same hotel room.
Oh, really? Aizo-san, can you give us a word, some word before departure?
This is my first experience to participate IODP Expedition. I'm as in organic geochemistry in Expedition 390, but I'm very interested in Rose's presentation, so I'm very exciting now.
That's very good.
Thank you very much.
So please enjoy the expedition.
ありがとうございます。
You are also welcome to make another presentation in the future in this seminar. Yeah, so if you have any other comments or questions, no? So can I pass to Abe-san?
Okay, thank you, Kuroda-san, and thank you, Rose. Wonderful talk. It was really, easy to understand, and actually, I really understood how I can read how to read the Lorentz diagram. So anyway, so please enjoy your expedition, and we wish your expedition success. And for 2 months, you're gonna have really good science there. Thank you very much all. Okay, so.
Thank you very much for having me. It's been a pleasure.
Thank you very much.
Thank you very much.
Again. Thank you. Okay.